If your instructor confused you when explaining how Taylor series work, I'm going to save you a ton of time. You don't need a whole semester to understand this, so make sure to watch the whole video and subscribe so you can crush this on your AP exam. Let's get started. For natural log of x plus 1, I want to center the function at a equals 0. And what I like to do is, I usually like a rule of thumb of taking 4 derivatives to see if I can get an idea of what the pattern will look like. But for the 0th derivative, the original function itself, I put a 0 notation here to make it a little bit more clear to me. And I'm going to evaluate this at x equals 0 because we're centering at 0. You'll get the natural log of 1, which will be 0 as the answer. Taking the first derivative, if you remember, the derivative of natural log of x is 1 over x, but we have the natural log of x plus 1 here. So we got to use the chain rule, and if you need a refresher, I've got a video on that. But basically, you get the outer function's derivative, 1 over x plus 1, times the inner function. And for the answer, I'm going to leave it like this, x plus 1 raised to the negative first. You'll want to stick around because I'll show you why I'm doing that down below. Evaluating this now at a value of a equals 0, you're going to have an answer that is 1. So we go on and we basically take the second derivative now, and now this is a polynomial function derivative. The derivative of x plus 1 to the negative first will simply bring the negative 1 in front, and you'll reduce the power by 1, resulting in negative 1 times x plus 1, all raised to the negative second. And with the chain rule, the derivative of the inner function is simply 1, but I didn't really show that here. So the second derivative evaluated at 0 will simply be negative 1 times 1 in parentheses, all raised to the negative second. I'm going to leave it like that because if I were to just show negative 1 as the answer, it may not be as clear with what we're going to do below. And that might be something your instructor didn't show you is, especially for Taylor series, sometimes the big mistake you can make is you simplify these expressions of products, and it makes it a lot harder to see what the established pattern will be. So moving on to the third derivative, you now repeat the polynomial derivative technique. So we'll get negative 1 times negative 2, in parentheses, x plus 1, all raised to the negative third. And once again here, I'm not going to simplify any multiplication. I'm going to leave it as is. And when I evaluate it at x equals 0, you'll get negative 1 times negative 2. Finally, for the fourth derivative, using the polynomial derivative rule again, the negative 3, the old power of x plus 1, will come in front. You'll reduce the power by 1 once again. And you can see now that when we evaluate this at x equals 0, we keep growing product terms in front of the expression, right? So the next thing I like to do is put this all in a table that simplifies everything and brings it all together. The top row will be the nth derivative and the bottom row will be the answer we got. So looking here, based on the bottom row, do you see the pattern of what the general nth derivative will look like? Pause the video and see if you can figure it out. Okay, tell me below if you got the answer right. And if you don't see it yet, that's okay. The next thing I like to do here, if it's not crystal clear, is in order to figure out what the nth derivative will be, I'm going to take the answers I got above, and I want to see what they have in common. So it's very clear that derivatives 2, 3, and 4 all have this negative 1 term in front. But believe it or not, the first derivative term does too, because 1 is actually the same as negative 1 raised to the 0th. The second derivative, if you were to multiply negative 1 and 1, would give you a negative result. And so the power of negative 1 would be 1 in this case. And for the third and fourth, you'll notice that if you were to multiply everything through, we keep going between a positive result and a negative result. And what I want to do here is, because for the Taylor series, we want to write a general expression that can create all these terms, I want to make sure this negative 1 is in all of my nth derivative terms. And so by doing so, what this allows us to do is, instead of worrying about the terms negative 2, negative 3, negative 4, to make it cleaner, I'll let the power of negative 1 be the only term that has negativity and make the other terms positive here. And then the other thing I want to do is, notice how for the fourth derivative, we've got products 2 and 3 here that I'm making positive, but I'm going to rewrite them in descending order as 3 times 2 versus 2 times 3. And the reason why I'm doing that is, looking at this very clearly now, you can see that two things are going on. One, we have negative 1 raised to a power for any general nth derivative. And two, what it's being multiplied like is looking very familiar to a factorial. So your nth derivative will actually be negative 1 raised to the n minus 1th power. times n minus 1 factorial. And this is a crucial step to not make a mistake on. I'm guilty of this too. We might rush and think, oh, it's negative 1 raised to the nth. But I would recommend you go back and you reevaluate this general expression for n equals 1 through 4 here and make sure you get the right result. But notice how the power of the negative 1 is always 1 less than what we are on for n. And similarly for the factorial. So for the general Taylor series expression here, we've got 1 to infinity of the nth derivative evaluated at a over n factorial all times x minus a raised to the n, where a is centered at 0 in this case. Now, pause the video and think about this and tell me, why did I not make this series start at n equals 0? And by the way, there are multiple ways of doing this. Maybe you did it a different way. There's no wrong answer or right answer here that you have to start at 1. But why in our case was it okay to do so? Okay, so you should have realized that at n equals 0, we got an answer that was 0. Now, we could have made a series that starts at n equals 0, but I'm leaving it off here because basically it's no different than just saying our answer is 0 plus a series starting at 1. Now, what you want to do is you want to plug in what the nth derivative of f of x is evaluated at a as the next step, which in the numerator we're doing that here, and that just comes from what we did above. Now, the final thing you got to realize here is we want to basically simplify this expression. Now, the really cool trick you can use is notice how the denominator here is a tad bit bigger than the numerator when comparing the two factorial terms. The difference is that you've got n versus n minus 1. But remember that n factorial is the same as n times n minus 1 factorial. And by factoring out the n, that allows us to simplify this expression even further.